Hey everyone, in this video I'm going to be deriving the 1D conservation of energy equation. I'm starting with the just integral form of the conservation of energy that I derived in another video that I'll link to in the video description, and I'll post a link on the screen here. So we're starting out with this integral form, and we have a volume integral, two surface integrals, another volume integral over here. And we're going to make some assumptions for this particular derivation. First assumption is that we're talking about 1D, because this is a 1D video. The second assumption is that it's steady state, and that means that we can get rid of this term here. This term goes to 0 because we don't have, nothing's changing with time, and this is a time derivative there. And the other is that we have no heat addition, or Q dot is equal to 0, which means that we can get rid of this guy here. So what we're left with then are these two terms here, two surface integrals, and I've written that down here. First term here plus second term here is equal to 0. I've rewritten that two-term equation up here again, and let's look at this schematic over here. We have it in black dashes. This is the control volume that we're looking at, and we're looking at in a 1D sense that we have flow at state 1 at the left side of the control volume going in, and then flow coming out of the control volume at the right hand side too, and I'll keep this color coded throughout the video. And you can see at state 1, at the inflow to the control volume, we have the density 1, energy 1, velocity, pressure, area, and then the surface normal. And the surface normal by definition always acts outward from the control volume surface, which is why this is going in the opposite direction. And then for state 2 over here, we have again rho 2, E2, V2, P2, A2, and the outward normal is acting out of the surface, which is in that direction. And we define positive x as that direction. So you can see that the outward normal on the 1 surface is acting in the opposite the positive x direction, while the surface normal for the 2 state is acting in the same x direction. And you'll note that we're going to have 4 terms in our equation when we first break this down, and we're going to have 4 terms, 2 terms for each integral, because what these integrals are saying is we just need to integrate over the control volume area. So we're going to integrate for this term, we need to integrate over the control surface. So we're going to integrate over surface 1 and then surface 2. So that's where 2 terms come from for this term. And then same thing over here, we're going to integrate 1 and we're going to integrate 2. So we're going to have 4 terms in our first equation that we write. Now there's a couple of issues I want to clear up before we get into the derivation, and the first is that this term here, this v squared term, is actually the velocity vector dotted with the same velocity vector. And so if you look at what the velocity vector actually is for each surface, we have v1, and it's a vector because we have the overbar there, and that's u1i in the x direction plus 0j plus 0k. So again, this is because we have 1D flow, okay? Same for v2, it's just u2i plus 0j plus 0k. So if you look at the v squared, it's actually the dot product of the 2 velocity vectors. So for v1, for the 1 surface of the control volume, it's v1 dotted with v1, which is I've dropped these 2 because we don't need them because they're 0. And so we have u1i dotted with u1i, and that's what we get is u1 squared. Same for v2, we just have the dot product, u2i dotted with u2i is equal to u2 squared, which is why this right here is written just as v squared. Now the second item of note is are the ds terms here, and these are also vectors. So this is the surface area vector, and we could break down ds into multiplication of the surface normal times a scalar dA or scalar area of this control surface. So for 1 and 2, it's just ds1 is just n hat 1 dA1, ds2 is n hat 2 dA2. And so the question then is, what is n hat 1 and n hat 2, or what are n hat 1 and n hat 2? N hat 1 is equal to negative 1. It's the unit normal out of the control surface. So it's negative 1 in the I direction, right? Because I said over here that it's acting in or pointing in the opposite direction of the positive x. So that's why it's negative 1 I. And n hat 2 then is pointing in the same direction as the positive x-axis, which is why we have positive 1i or plus I. So we can rewrite ds1 from here. We can bring this down. ds1 is equal to negative dA1i, and then ds2 is positive dA2i. And after we do the integration over the surface area, we end up with the ds1 integrated over the control surface at 1 here is going to be negative a1i, and then same for ds2 after integration is going to be plus a2i. And so we can move on and kind of plug these into these integrals up here. Now let's look at the actual integration here, breaking these two terms up. We can start out with this term for surface 1, and we're just going to plug in these terms here over to here. So we have rho 1 times e1 plus 1/2 u1 squared from before, and then we have this v dot ds is going to be the u1i dotted with the negative a1i as discussed before. And then we're going to move to this term for surface 1, which is p1 times, again, v dot ds, same term from over here. And then we'll move to this term again for surface 2, which is down here. Plug those values in. Now we have u2i dotted with plus a2i. And then this term for surface 2, which is p2 times that same term from over here. And from what I mentioned before, we can take the u1i dotted with negative a1i, and that's just multiplying these two together because they're the same component, the I component. So we have negative u1a1, same here. And then down here, since we're dotting with a positive area term here, we have plus u2a2, same over here. Now here I've just taken those terms that were shown below the equation and just moved them into the actual terms here. So you can see we have the negative rho 1 u1 times this here, plus a negative, so both of the side 1 terms are both negative, and we have plus this term here, it's positive, plus this term here, positive, is equal to 0. And now that we're talking about 1D flow, we can say that the area 1 of surface 1 is equal to area of surface 2 is equal to A. So because all of the areas are the same, they actually, we can divide by the area on both sides, and all of the areas will drop out of this 1D equation. Okay, so all I've done here now is, since these terms before were negative, I just moved them to the other side, but then wrote this side first. So now we have side 1 here, side 2 here, the equal sign. So this side 1 is equal to this side 2, and you'll notice that there's no areas anymore because we got rid of them. And so now what we need to do is to bring the pressure term into the parentheses for both of these. So I want to bring this P1, U1, whatever, into here, but I can't just do that just yet. First we need to multiply the pressure terms by either rho 1 over, that should be rho 1, or rho 2 over rho 2, which is just 1. So we're just multiplying this term by 1, and it happens to take the form of rho 1 over rho 1. And then we're also multiplying this term here by 1, so we're just multiplying by rho 2 over rho 2. So how did that help us? If you look at this term here, you can see that we want, outside the parentheses here, we have rho 1 u1. Here, now we have rho 1 u1. Here, outside the parentheses, we have rho 2 u2, and over here we have rho 2 u2. So what we can bring inside the parentheses then is this p1 over rho 1 into here, and p2 over rho 2 over on this side of the equation. So when we bring that term inside the parentheses, now we have this equation here, rho 1 u1 times this term in the parentheses is equal to rho 2 u2 times this term in the parentheses. And from 1D mass conservation, I'll post the video that I did for this one, the derivation, in the video description or up here. We get that rho 1 u1 is equal to rho 2 u2, and this is also because these areas A1 and A2 are equal to each other, because usually you see this as rho UA is equal to rho UA. So if that's the case, then these two terms right here are the same and they drop out of the equation. And what we end up with tentatively right now is E1 plus 1/2 U1 squared plus P1 over rho 1 is equal to E2 plus 1/2 U2 squared plus P2, I'm messing all these up, over rho 2. So you can leave the conservation of energy equation in the form shown here, but a lot of the time, especially when you're dealing with flowing fluids, we can use what's the property enthalpy, which is defined as E plus PV, or then the same as E plus P over rho, because V, the specific volume, is just the inverse of the density. And so if we plug that into this equation up here, you can see this E1 plus P1 over rho 1, that's going to be enthalpy at 1, E2 plus P2 over rho 2, that's enthalpy at 2. If we plug that in, then we get the final form of the energy equation couched in terms of the enthalpy as H1 plus 1/2 U1 squared is equal to H2 plus 1/2 U2 squared. Thanks for watching.